We've been doing a lot of stuff with matrices. We've been, especially since you've seen in the exam, everything was dealt with the matrix. We took determinants of matrices. We've solved system of equations with matrices. We found the inverses of matrices. We've added, subtracted, multiplied, transposed, took the trace of matrices. We talked about linear transformations. So we started getting into a bit more of a theoretical aspect of what matrices are and how we can apply them and what's the significance of those matrices with respect to linear transformations. So we've been doing a lot of matrices talk up until this point. And we've mentioned during that time, we've mentioned a bit of how we have what are called vectors, right? We talked about a matrix multiplied by a column vector, and that results in another column vector. So in a sense, we've been dealing with vectors embedded into matrices. And now we're going to be heading into the world of vectors. So let's start with what a vector is. So for those of you who've taken physics classes, that's like one of the most fundamental units in physics. So what is a vector? Anybody? Magnitude and direction, right? Force with magnitude plus direction, right? So when you talk about vectors in physics, you talk about force, you talk about velocity, acceleration. What else is a gravity, right? Has a magnitude and direction. So a vector is oftentimes used to describe a physical phenomenon such as force, acceleration, gravity, which is gravitational force, same thing, right? Etc. That has a magnitude, a magnitude and the direction. So it has two things. As a magnitude and a direction. But of course, mathematicians, they don't just stick with the physical, right? They usually abstract this notion from the physical. So then they speak about vectors just in the sense of what vectors are. So it doesn't necessarily need to have a physical connection. It is just a representation of in a sense, we treat them as arrows, and these arrows have an initial point and so this is a mathematical perspective of a vector. It still has a magnitude and it still has a direction. But we give it a geometric representation with an arrow, or what's called array in mathematics. And so we have an initial point. We call this the tail. And this here, the top of the arrow, we call it the terminal point. And this is the tip. And there's something called the tail to tip method, which is used to explain how you add vectors to one another. So you see the length of this, right? The length of vector is the magnitude of the vector. So in our world of mathematics, vectors have a certain length, and that length represents the magnitude of that vector. So the longer it is, the larger the magnitude, the smaller it is, the smaller the magnitude. And for those of you who've taken multivariable calculus, you probably have seen that with slope fields or differential equations when we talk about slope fields, or when you talk about vector fields in multivariable calculus, you talk about vectors and how every point on this two-dimensional space or in a three-dimensional space, at every coordinate, there's a certain arrow or vector attached to that coordinate with respect to whatever vector field that exists. And of course, the direction, right? The direction is denoted by the angle that you have this vector pointing towards. And normally we define the horizontal axis to be where, to be 0 degrees or 0 radians. And from there we have a direction, we have an angle that's made with that horizontal axis, and that would indicate the direction of my vector. Okay, so this is the way we view vectors from a mathematical perspective, particularly I would say a mathematical geometric perspective. So this is when you have a vector in R2 space, which is the X and Y plane. You can also have vectors in R3 space, which we have the X, Y, Z plane. And we have a three-dimensional representation of the vectors. But then what we tend to do is we extend that notion into a higher dimensional space. Now, once we've reached the fourth dimensional space, we can no longer use our physical intuition or understanding of our three-dimensional world to understand a four-dimensional space. And so we get to do what's called an abstraction. We tend to try to abstract the idea of vectors into a higher dimensional space. So at that point, we treat vectors as simple n-tuples. We talked about n-tuples before. So the n-tuples are just a set of coordinates with n coordinates in them. So this is usually the way you've come across vectors, right, in physics, as a magnitude, as a force, or as a physical action that has a magnitude and a direction. That's how you usually are introduced with it. And then in mathematics, we treat this as arrows, vectors, right, with a length and a direction. And then we tend to just get away from geometric understanding of it and deal with it as purely coordinates. So that's the level of abstraction. We start with a physical thing, and then we're just dealing with the numbers, the set of coordinates. So this is a mathematical geometric way, and then this is a mathematical abstraction of a vector in Rn. So this is a vector V. I'm gonna call this V. This is and usually we denote vectors with letters, and then we have a little arrow on top. This is my first coordinate, my second coordinate, all the way to my nth coordinate. So you see this? These are three ways to interpret a vector. A vector is a physical phenomenon that has a magnitude and a direction. That's one way. A second way is that it's an arrow in space that has a certain length, has a certain direction, and we consider that to be a vector. And then we generalize this idea into dealing with a vector just as a n-tuple. An example of an n-tuple. For now, we're going to be sticking with this perspective of a vector. We're going to be dealing with it as a geometric representation in R2 and R3 space. And then the idea is we're going to go into the higher level dimensions a bit later. Okay. So we'll be talking about vectors in R2 and R3. So the first thing is, how do we add vectors? Vector addition. So let U and V be vectors. What is the sum of U plus V? We talked about this very briefly in one of the lectures. So let me add some dots here. Let's look at examples, concrete examples. So remember, U, we can treat it as a n-tuple, right? Let's look at 1, 2. So what is that going to look like? 1, 2. So this is my vector U right here. My terminal point is at the coordinate 1, 2, and my initial point is at the origin 0, 0. And then let me use another vector, V. I'm gonna say this is 5, 3. 5, 3 is 1, 2, 3, 4, 5, and then 3. Boom. So we have two vectors. You see, I'm in the two-dimensional space, R2. I'm in R2. Every point in R2 has two coordinates, X and Y. I have my vector U, and I have my vector V. And now what I want to do is I want to find the sum of U and V. So U plus V. Right. Doesn't that feel natural to you, Sam? Doesn't it feel natural to add vectors as 1, 2, and you add it by 5, 3, and you add it component-wise? This is the same thing as what we're adding matrices, a column vector. You see? It's the same idea. Right? It follows. It just follows. So this becomes 1 plus 5, 2 plus 3. This is 1 plus 5, 2 plus 3. Do you see how both representations gives me the same idea? It's the same. So the result would be what? U plus V is the vector whose x coordinate is 6 and whose y coordinate is 5. So I have somewhere here. This is 6 and this would be 5. And then if I draw this line, boom, I have the sum, U plus V. So adding vectors is almost a natural thing. It's a very natural to add just the x values together, make that the new x coordinate, and add the y value, add y coordinates together, and that would be my new y coordinate. But I also want to show you the geometric relationship that that vectors have when you add them. So when you add them, you treat it as two separate vectors, and you apply what's called the tail to tip method. For those of you who've done physics, you probably have seen this already. The tail to tip method is you include one. So another thing about vectors is that you can move them. Oops. You can move them in space as long as the length of the vector stays the same and the direction is not changed. I can move this wherever I would like, wherever I like in space. And the vector is still the same vector, right? I can move this anywhere I want. It's the same. So I'm adding u plus v. I'm taking this vector here and I'm placing it on the tip of the other vector. So all I did was I moved it up. And the idea is when I do so, the tail to tip method, so the tail to tip method, which means that now I'm going to connect the tail of the connected vectors. I'm going to take the tail and then connect it to the tip of the connected vectors. In doing so, I get the result. I get this sum. In physics, it's called the resultant, right? When you talk about resultant forces, we have two forces that are, or more than one force that are applying to the same object. What's the result? So this would be called the resultant. So u plus v is also known as the resultant in physics. And so this would be u plus v. This is v. So if I add u plus v, it would be the same thing as v plus u. So the commutativity of vector addition holds. And so then we can also apply the same way this way. I can do v and then add u after it, or I can do u and then add v to that. I'd still get to the same point. I still get to the same resultant, the same sum. Does that make sense? Has everyone seen this, or is it the first time? Good. So we know how to add vectors, and this idea of the tail to tip can also be applied to three-dimensional space as well. Good. I'm glad you've seen it in physics. Good. So that's how we add. Now, how about when we subtract? Subtracting vectors. How do we subtract vectors? So let's say I have another vector here, u. I'm gonna call this 1, 5. And then v, I'm gonna call it 4, 3. So 1, 5 would be 1. This is 1, 2, 3, 4, 5. So I have this vector here. I want this to be straight. So this is u. Then I have v, right? So 1, 2, 3, 4, 3. So how do we add or subtract vectors? So if I want to find what is u minus v, it should also follow from addition. We're subtracting component-wise. X components with the y components, right? So we should get 1 minus 4, 5 minus 3. It should be negative 3 comma 2. That should be my result. So I'm going to get something here. So 1, 2, 3, comma 2. So I'm going to get something like this. But so this is the result of subtracting v from u. And again, this is v here. But how does this relate? How does this one here relate with these two vectors? The way this vector here relates to these two vectors by adding them, by moving them in such a way that when you connect the tail to tip, I get that result, that resultant. How does this make sense with this? How does this make sense with subtraction? Does anybody know? Has anyone done this?
Is it when you reverse the one you're subtracting, the direction?
Yeah, that's right. So subtraction, remember, subtraction is really just adding by the inverse, in this case, the additive inverse. So u minus v is the same thing as saying u plus negative v. Now, what does negative v mean? What does the negative v mean? So v in this case would be 4 comma 3, right? What if you do negative v? What would that look like? Negative 4 comma negative 3. So then you have the same vector. It's just that now you're what? You're going the opposite. You're going the opposite direction. So this v here, this would be negative v. The vector negative v is the vector that's going in the opposite direction as the original vector, directly in the opposite direction. But as you notice, it has the same length. And so then if you want to do u plus negative v, what is that going to look like? I have this vector and I'm doing the tail to tip method. I'm placing it right on top here. And as you can see, it fits perfectly. And then when you do the v, I should maybe write this. This is u, and this is negative v. So when I add u with negative v, I'd use the tail to tip method, and I find that vector. You guys see that? And remember what I said, these vectors in space can be moved around in space as long as the direction and their magnitude stays the same. So this vector can also be seen here. So when you do u minus v between two vectors, the difference, the vector that results in the difference is just the vector connecting those two vectors. And it's in the direction of the positive vector. So u minus v, I connect them, and I put the arrow towards the positive vector u. And if I add them, u plus v, I'm just going to connect it like this. So what does this become? I don't know if you see it. What kind of shape is formed? Does anybody see it? What's the shape?
Parallelogram?
It's a parallelogram. So when you add Well, a trapezoid, not quite. But when you add the vectors and subtract them, you get the diagonals. You get the diagonals of a parallelogram. You see that? So I'm talking about this shape here, this one here. So one of the edges, one of the sides is U, the other side is V. These two sides are parallel. This should be V, pardon me. So we got these two sides being parallel. These two sides are parallel. So we have a parallelogram. And let me make sure you guys see that. And so the smaller diagonal is the difference. So the smaller diagonal of parallelogram is the difference of the vectors. And the longer one, maybe different color, let's see, yeah. The longer one this one, longer diagonal is the sum. But of course, this is for this particular example, because you can have vectors that are not, let's say the angle between them is not acute. You can have angles that are between two vectors that are obtuse. And so the opposite would be true. The smaller diagonal. So you can have vectors when you have something like where the smaller diagonal is actually the sum and the longer diagonal would be the difference. So you can have different things. I'm just saying in this particular example, the longer diagonal is the sum of the two vectors and the small diagonal is the difference. The idea is whenever you have two vectors and you're adding them, you can span, what you can create is a parallelogram using those two vectors. And the diagonals of those two vectors are either going to be the sum of the two vectors or the difference of the two vectors. And as you can tell, the actual computation of adding and subtracting is pretty straightforward. You're adding by components. So by coordinates, x coordinates add up to the x coordinates and the y coordinates add up to the y coordinates. Okay, so that's vector addition. Great. Now, what if we have, so we can have things in space, right? So what if we have, it says finding components of a vector. So what if I have an initial point I'm gonna call this initial point P1, 2 comma negative 1, 4. And I'm gonna use the terminal point I'm gonna call it P2. And this would have the coordinates 5, 4, negative 3. What are the components of V? So my vector V is defined as the ray that connects point 1 to point 2. So how would we write the components of this vector? The components meaning the coordinates. So V I'm taking the ray from point 1 to point 2 in the direction of from point 1 to point 2. So point 2 again is the terminal point, and the point 1 is the initial. Has anyone seen this? Yes, good. How do we do it? What would be the components? For those of you who've seen it.
The sum of the points. I think I'm kind of foggy on it, but
Yeah,
I'm pretty sure you
it's
start
not
with that.
this. It's not the sum.
It's not? Okay.
No. Uh, remember what we talked about. It's think about point 1, P1 being some point in space, and then P2 being another point in space. And I want to connect the line that connects those 2 points. So the line that connects these 2 points is actually going to be the difference between these 2 points. It's going to be the difference. Treat this as a vector and treat this as a vector. Subtracting these 2 vectors would give you the line, the vector that connects the endpoints of these 2 vectors. So you're actually subtracting them. Now, how are you subtracting them? You're subtracting them. P2, you're subtracting P1 from P2. So you subtract coordinates of P1 from P2. So P2 has 5, subtract that from 2. P2 has the y coordinate being 4, subtract that with -1. And then P3, the third coordinate of P2 is -3, subtract that with 4. And the result is 3, 5, -7. This is the vector that connects P1 to P2. Let me see if I can actually show you this. I remember last time I tried to show you. Let me see, where is it? Okay. I tried to show this to you guys, but it was kind of difficult to do that. 3-dimensional. You guys see it, right?
Yeah.
Let me see if I could do this. So we have 2, -1, 4. So I'm gonna treat, how should I treat this? So the green will be my x-axis, the red would be my y-axis, and the blue would be my z-axis. So I want to draw a vector. Let me see the vectors. A vector, awesome. You see, I'll make sure how they make it. Okay, so that took a little too long. Okay, so this is, let me see if I can do a vector here. So mine was what, 2, right? -1. Mm-hmm. You need 2 of these, huh? Yeah, actually, this is still kind of difficult to do because it's hard to choose a point in space like this. 2, -1, 4. Yeah, this becomes kind of difficult to do. But anyways, I'll see if I can figure out how to use this to create those vectors. But the idea is, let's just use the regular two-dimensional perspective of a three-dimensional space. Try our best that way. So this is X, this is Y, and this is Z. So if I have a point in space, 2, -1, so 1, 2, this is 2. And then -1 would be here. And then we have 4. So it would be 1, 2, 3, 4. So I would have something. I'd have this point here in space. This is P1. And then P2 will be 5, 4, -3. So it'd be 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. So you'd have another point here in space somewhere. This would be P2. And what I want to do is I'm going to draw the line of the vector from P1 to P2. This would be my vector V. This would be V. P1 to P2. And that vector has the dimensions 3, 5 components, 3, 5, -7. So if I draw it, if I connect the points P1 and P2, this would be the vector in space. But this vector, remember what I said, you can move this vector all around in any and place it anywhere in space as long as the dimension, the magnitude is the same and the direction is the same. So the components of this vector, if I were to connect the terminal point, so this would be my terminal, right? Terminal. No, pardon me, this is my initial. If I put my initial point, as the origin, if I move this and put this here, then the tip, the terminal point, the tip would have the coordinates 3, 5, -7. So that's the idea behind having 2 points in space and finding the vector that's in between the 2 points. Okay. Also, this should be pretty straightforward. Okay. And of course, we have things that are called the zero vector. We talked about the zero vector before. So what is a zero vector? We usually denote it with a bold 0 or a 0 with the arrow on top. It's the coordinate that has zeros everywhere in its n-tuple representation. So in two-dimensional space, right? In two-dimensional space, the 0 is that point on the origin. In three-dimensional space, it's the same point where all the axes meet. It's going to be a point, a single point. But that's still a vector, though. It's just a simple 0 vector. Okay, so I'm just saying that this exists. The 0 vector exists. So we have 0 vectors in space. Okay. So yeah, it's just the origin in Rn. That's what the 0 vector represents. Okay. So here are just a few properties. Properties of vector arithmetic. So the first one is you have a vector u plus a vector v. So if, I should write this, if u and v are vectors in Rn and k m are scalars. And remember, what's the word scalar mean? Anybody? What does the word scalar mean?
A non-variable?
It's a non-variable. It's not a variable. It isn't. But what is it?
I don't want to say constant because would that be right? I don't know.
Yeah, it is a constant.
Okay.
But in relation to vectors, do you see the relationship between a scalar and a vector? So it is a constant. We treat them as constants in mathematics. It's a constant number. In particular, it's a number that has just a magnitude. There is no direction. So that's what makes scalars different from vectors. Vectors has a magnitude associated with the direction, but scalars only have a magnitude, which is just a number itself. There is no direction to it. So that's why people call speed as a scalar compared with velocity. Velocity is a vector. The difference is you can say I'm going 35 miles per hour. That's a particular quantity, and that's just a number. So that's a scalar representation of how fast you're going. But if you're saying you're going 35 miles per hour northwest, then that becomes a vector because you're dealing with direction. Okay, so the distinction between vectors and scalars should be clear. So of course we talked about the commutativity, right, aspect. There's a few others. There's also associativity. So if I have three different vectors, I should also include u, v, and w. So if I have u plus v plus w, if I add u plus v first, and then I add w to it, it's the same thing if I add v plus w first, and then u. So associativity also exists. And the commutativity aspect of vectors addition and the associativity aspect of vector addition really just follows from the commutativity and associativity of just regular numbers. Just adding numbers, it's commutative and it's associative. So if you're adding vectors, which results in just adding the components, it still leads to the same result. And if you add a vector to the zero vector, obviously you get back u, or you can say it's also commutative, right? So this is like the identity. This is the identity element that exists. The identity, the additive identity here would be 0. If you add by the identity element, you get back the thing that you started with. So u plus 0 is just going to be u again. If you add a vector to its additive inverse, you get the 0 vector. So this is additive inverse. For those of you who plan to take, how come 2 U's are allowed? What do you mean by two u's?
I think he means in the second part of 3, it says 0 vector plus u vector plus u
Oh,
vector.
pardon me. I meant to say equals. Thank you. Yeah, it's not u. It's not 0 plus u plus u. It's 0 plus u. U plus 0 gives you u. For number 4, u plus negative u equals 0. That's the additive inverse. Now, what I was going to say is that for those of you who are, interested in the mathematics of things, for those of you who might major in mathematics, in addition to whatever it is that you're doing, computer science or education or business or whatever it is, right? There's something called abstract algebra. In a sense, you've been learning abstract algebra since the moment you learned about what algebra is. But particularly with linear algebra, when you learn about the vector spaces and all these different properties, you can also generalize this. The idea of commutativity, associativity, additive identity elements, additive inverse elements, these ideas can be extended beyond the realm of vectors. And so then that's what we talk about. That's when they talk about what are called groups and what are called rings and what are called fields. And that's more of an abstract notion. So the reason why I bring this up is because abstract algebra is the generalization of everything that you're going to learn in linear algebra. It's just generalized to just an algebraic, whatever an algebraic structure that you have. This is a very specific kind of algebraic structure because we're dealing with vectors, adding vectors, right? Up until this point, you've also been learning how to add just numbers. So you're adding numbers, you can add them, you can switch around the order, you can add something that's a negative of it, right? We know how to do these things with numbers, and now we're applying this to vectors. But you can also apply this to a more generalized notion of what algebraic properties and operations are. It doesn't only just apply to addition of numbers, and these ideas don't only apply to addition of vectors. It can be applied to a more broad spectrum of operations. And that's where abstract algebra comes into play. And abstract algebra unifies all these things together. And it's very nice to learn. And also people who do physics, there's a lot of abstract algebra notions in physics as well. So that's my little 2-minute spiel on abstract algebra. So let's continue with this. So this is, okay, next would be K times U plus V. So you see this idea of distributivity also applies here because it applies over this the distributive property over just regular numbers. So if you have a scalar K and you're adding it to a sum of two vectors, it's the same thing as saying the scalar K times a vector plus a scalar times the other vector. Also, if you have a sum of two scalars and you multiply that by a vector, then it's the same thing as saying the same idea, right? You can also distribute the multiplication of vectors. So you multiply the scalar k to the vector u plus the scalar m times the vector u. You can also do that as well. 7, k multiplied by m times u. There's also an associativity for the multiplication of scalars. I can multiply k multiplied to m times u, or I can multiply km first and then multiply that to u. And then lastly, one u vector is just equal to the u vector, obviously. Okay. Yeah, and one thing I want to just briefly touch upon is What is scalar multiplication? Scalar multiplication of a vector. So if I call a vector v, and I have the vector 1, 2, one comma two, I got this vector here, right? This is v. Now, what happens when I do 3v? What would 3v be? Well, I'm just multiplying 3 by 1, 2, right? Which means what? I'm multiplying 1 by 3 and 2 by 3, and I get 6. So 3v is what? 1, 2, 3. 1, 2, 3, 4, 5, 6. I have somewhere here. So that would be 3v. This would be v. So what is scalar multiplication? When you apply it to a vector, you're just extending it or magnifying it. If you do half of v, you're going to be, or multiply v by a fraction less than 1, you're going to be minimizing it. The point is, though, all you're really changing is the magnitude. So scalar multiplication only changes the magnitude of a vector and leaves the direction unchanged. So you're either maximizing, you're either magnifying the vector by the scalar that you multiply by. You can be minimizing it, or you can be extending it in the other direction if you do a negative. Okay, so that's what you're doing when you're multiplying a vector by a scalar. You're either making it bigger in the same direction, you're making it smaller in the same direction, or you're flipping it in the negative direction, in the opposite direction of a vector. Okay. Now you've mentioned, I've mentioned this before. Now this idea of linear combinations is very important in linear algebra. And as we talk about vector spaces and such. So linear combinations. What are linear combinations? So definition, if W is a vector in Rn, so already we know it's going to be n tuple, has n coordinates, n components, then W is said to be a linear combination. It's said to be a linear combination when what happens? Of the vectors v1, v2, all the way to I'm gonna call this vk in Rn. So let's suppose I have a vector w in Rn and I have k other vectors in Rn. called V1, V2, VK. W is considered to be a linear combination of these guys if it can be expressed as the following. W is equal to some scalar multiple C1 of V1 plus some scalar multiple C2 V2 plus some scalar multiple C3 V3 plus some scalar multiple CK VK. Where what? Where C1, C2, all the way to CK are scalars, AKA real constants, real value, real constants that are real numbers. Very important concept, guys. Very important. A linear combination. So we say W is a linear combination of these vectors, V1 through VK, if you can add V1, V2, V3, and VK and multiply scalars to each of them and add those products together to give you the vector W. If that's the case, then W is a linear combination of V1, V2. Oh, this should be V2, pardon me. V1, V2, V3, all the way to VK. So that's just the way we define linear combinations. Does that make sense? This idea will come up again and again, especially when we talk about what's called the basis of a vector space. Okay, just letting you guys know about that. All right. So a simple example of this, for example, is you give me any vector. Let's call it W. Let's call this 4, -2, +3. And let me just give you a note. Any vector in Rn can be expressed as a linear combination of E1, E2, En. Remember what E1, E2, En are? They were called the standard basis vectors. Remember, E sub I is equal to a whole bunch of zeros except for the ith position. That's what E sub I stood for. 1 is in the ith entry, zeros everywhere else. Okay. So can we write W as a linear combination, right? W as a linear combination of E1, E2, E3. We've done something like this before. So how would you write W as a linear combination of E1, E2, E3? What scalar should we multiply E1? Right, by 4, right? So I can write it like, I can write W this way, guys. I can write it as 4 E1 plus, or I should say minus 2 E2 plus 3 E3. And that's it. This is a linear combination. W is a linear combination of E1, E2, E3. Now, in mathematics lingo, right, we use E1, E2, E3, E4, E5, En, and so on and so forth. But for example, there are certain professional professions, careers, physicists, engineers, they use another notation for this to represent the same thing. So in some spaces, they use the I instead. They use I hat, J hat, and K hat to represent E3, which is 0, 0, 1, which is J hat is E2, which is 0, 1, 0, and I hat is E1, which is 1, 0, 0. So we can also have written W as 4I hat minus 2J hat plus 3K hat. And again, this I is not the I that we're dealing with here is not the complex imaginary unit. So this I is not. So just note that, okay? So note I hat is not the square root of -1. It's not. We're just using the 3 letters that are next to one another, I, J, K, by convention. Okay? Okay. So far, pretty rudimentary, pretty basic stuff, right? Some of you have seen most of this in other classes, whether it be in physics, because we talked about vectors. So that's the first thing you guys talk about, how to add vectors, how to subtract vectors, how to multiply vectors. So in physics, you've seen it. You've probably seen it in multivariable calculus for a fact. And so what else can we talk about with vectors besides adding them, subtracting them, multiplying them? Well, we talked about something about the length, right? So the length is also, there's a word for that in mathematics called the norm. The norm of a vector. The norm of a vector is simply is the length of a vector. So this idea of distance, length, is important also, is also important in the world of vectors. And what do we use to denote norm? We denote norm, we denote the norm of a vector, V, by, we use 2 vertical lines to indicate like kind of like absolute value. Some textbooks use an absolute value, like absolute value symbols, but typically, conventionally, it's 2 of those on each side. Now, without getting too abstract also with this idea of norm, norm is a way to define, you can say distance. It's a way to define distance. Now, what gets interesting with the idea of norm is that there's more than one way of calculating distance. We have a natural way to calculate distance. Does anybody know how we calculate distance? How do we calculate distance in two-dimensional space?
I feel like we learned a formula for this ages ago, but I don't remember anymore.
Yeah, there is a formula, but even if you tell me the formula, it doesn't really answer my question. Because the formula represents something. And what is that something that that formula represents? So if I want to figure out the distance, right, between 3, 4 and 0, 0, forget the formula for now. How would you do this? How would you find this distance?
The difference between the related. Oh, I'm sorry. Go ahead, Baldwin.
Oh, go ahead.
Yeah, anyone, Baldwin, Sam. How would you define
I was gonna
distance?
say you could do a Pythagorean's theorem.
Wow, yeah. How do you do that?
So we would, I guess the x-axis, we could take it and make a right angle.
Right. So you're saying, oh, wait, distance here is defined to be
Yeah.
the hypotenuse of a right triangle, because you can exploit the geometric nature of what's called the rectangular coordinate system. You can bring this horizontally, vertically, and you can bring this horizontally, and you create a right triangle. And one of the sides is going to be the y coordinate, which is 4. The other side would be what? 3. And what's so nice about this particular triangle, that's the right triangle, is that these numbers satisfy the Pythagorean theorem in a very nice way. This is 9 plus 16, which is 25, which equals the square of the hypotenuse, which would be 5, right? Because 25 would be d squared, so d would be 5. So the distance between these 2 points is 5. But that's a particular definition for my distance. In your head, distance is the smallest path from one point to the next. That's according to many of our concept of distance. But that's not the only way to define distance. That's my point. My point is there's different ways. There's other ways to define distance. There's different metrics, another word people use to define what a distance can be. So our particular distance is called the Euclidean norm. And that has to deal with what was mentioned. The Pythagorean theorem is embedded in the formula that Sam was trying to explain. So Sam, do you think you can figure out that formula? So watch this. Hopefully after this, you don't have to ever memorize the formula. You can always, in a way, reason it out or derive it every time. So like, suppose I get something like this. Let's see, 1, 2, 3, 4, 5. This is -1. So I have a point here. And then let's have a point 5, 5. And I have a point -1, -3. And I want to find the distance between these 2 points. What do I do instead now? How would I find the distance?
I know this isn't what you're looking for. It's kind of a cop out, but can't you realign it to the origin and still calculate Pythagorean if you really wanted to?
Yeah, that's what I was thinking as well.
It's a great idea, but hopefully you see you don't need to do that. That's a great idea. But you
Yeah, I
don't need to do
figure.
that to get the
I
same
just don't
idea.
know.
You can
I
still do
just
the
can't figure
Pythagorean
out the-
theorem. Pardon me?
Sorry, Professor. I was just saying, yeah, I'm sure that's not what you're going for, but I can't quite figure out the other way you're trying to pin us to figure out.
Well, what did we do here? We just extended this line downward, right? And extended this line to the right. And then what do we create? A
You
right
get-
triangle?
well, yeah.
What stops us from doing the same thing here?
Oh yeah, good point. It doesn't matter. It's still X
It doesn't
amount of
matter.
distance from one point to the other.
It does not matter. Do you see that? So then what really does matter is the difference between the y coordinates and the difference between the x coordinates. That's what really matters. If you were to relocate this whole thing, right, where this is the origin, you kind of gloss over that reality that that doesn't matter. It doesn't matter where these 2 points are in space. I can always create a right triangle where one of the sides is the change in the x values and one of the sides is the change in the y values. How do you find the change in the x values? You do x2 minus x1 or y2 minus y1. In this case, what I'm going to use is the bigger x value, which would be 5 minus -1. This is 6. I'm going to use the bigger y value. 5 minus -3 is 8. If I were to relocate these 2 points, I would get the same thing. I would get a point. My coordinate here would be 6, 8. And this here would be 0, 0. I move all the y coordinates up by 3 units. So this will be 8 because I'm adding 3 to 5. And I'm moving -1, right? I'm moving 1 unit to the right. So I move this unit, this x coordinate to the right. That would be 6, 8. And you'd have a right triangle 6 by 8. And by applying the Pythagorean theorem, what would you get? 6 squared is 36, 8 squared is 64, 64 plus 36 is 100, the square root of 100 is 10. The distance between those 2 points is 10. Now, do you see where I'm going with this? Now, suppose I'm not specified, right? You see the algorithmic portion of this? It's a lot of algorithms here in mathematics. So like, let's say I have a point here in space and another point here in space. I don't know what they are. I just know they have coordinates.
Oh, I see. And then now we can just solve for,
Right? This is
Yeah.
x1, y1. This is x2, y2, right? What am I looking for? I'm looking for what? The distance d. I want to create an algorithm that you give me 2 points, such as this, x1, y1, x2, y2, and all you have to do is tell me what do I need to do in order to find that distance? What you could do is exactly what you guys said. Oh, you can relocate this and make this in the origin. So you would subtract everything, the x coordinates by x1 and the y coordinates by y1 to get 0, 0. And this would be what? What would this be? x2 minus x1, y2 minus y1. Do you guys see that? Or you can just create a right triangle. Same idea. What do I want to figure out? The change in y. What do I want to figure out here? The change in x. What's going to be the change in x? Well, whatever x2 is, subtract that with x1. Change in y, well, whatever y2 is, subtract that with y1. Now, what do you have? A right triangle, and you can apply what? The Pythagorean theorem. That's right. Baldwin, you got it.
It's so much
this would
more
be what?
inherent that way.
Pardon me?
It's so much more inherent that way without having to move anything.
Yes. By the Pythagorean theorem, the change in x squared plus the change in y squared gives you d squared. And then what is the change in x? x2 minus x1 squared plus y2 minus y1 squared equals d squared. And then that's where you get the famous distance formula. you take the square root on both sides and you get that the distance is equal to the square root of x2 minus x1 squared plus xy2 minus y1 squared. This is a distance. The distance formula is inherently the Pythagorean theorem. That's why the Pythagorean theorem is so crucial. Without it, we wouldn't be able to define distance in such a precise way. So whenever you see the distance formula, you're really just reinstating what the Pythagorean theorem is. And so then how does that apply to vectors? Well, it has everything to do with vectors. So if I have a vector v, and I have 3, 5, for example. So this is 1, 2, 3, 1, 2, 3, 4, 5. And I have this vector here. And I'm gonna call this v. But I want to know the norm of v. What would be the norm of v? Well, it's the same idea as finding what?
The origin. Yeah.
Distance between 3, 5 and the origin 0, 0. Right? So then this would be what? The square root of, well, what is the horizontal component of the vector? It's 3. What's the vertical component of the vector? It's 5. So this is the square root of 3 squared plus 5 squared, which is the square root of 9 plus 25, which is the square root of 34, and whatever that may be as a decimal. That's going to be your norm of v. That's going to be the length of my vector. So in R2, if v is defined as v1 comma v2, then the norm of v is equal to the square root of v1 squared plus v2 squared. Does that make sense? Finding the norm of a vector in two-dimensional space is taking the square root of each of those, it's the square root of the sum of the squares of the coordinates. And why is that? Well, you just go back to the idea of how to find distance between 2 points in two-dimensional space utilizing the Pythagorean theorem. That's where the square root comes into play, and that's where the squares come into play. Now the idea, what happens though in R3? This is just in R2. What happens in R3? Norm in R3. How do you find the norm of a vector in R3 space? So let's suppose I have a vector. Let me see, 3, 4. So what if I have a vector like that comes out and call this vector v? What if v is 3, 4, 5? So I'm in the first quadrant, octant, I should say. I'm in the first octant. This is 3, this is 4, and this is 5. That's why I drew this kind of like this box with the dimensions 3, 4, 5. And then Mir says the length of z squared added under the radical. That is right. Now, Mir, how do you know that? How did you know that you just have to add that one dimension, that one extra dimension? Very good, Mir. That's right. That's right. So the reason why is because we're applying the Pythagorean theorem twice. You can consider this as a two-dimensional problem first. And then you can consider this as another two-dimensional problem here. So to find this side, you know this side 3. You know this side here is 3. You know this side here is 4. So then this side here would be the square root of 3 squared plus 4 squared, which is 5. But then how do you figure out this extra side, the dimension, how do you figure out the hypotenuse of this triangle here? Well, you know this hypotenuse of the blue triangle is the base of the other right triangle that I have here. You know the height here is 5. So the norm of V is going to be the square root of, I'm just going to break this down first. It's really the square root of 3 squared plus 4 squared. This thing here is squared plus 5 squared. So when you take the square root of something squared, it becomes just 3 squared plus 4 squared plus 5 squared, which is the square root of 9 plus 16 plus 25, which would be 34, which would be what, 69? Because 34, right? No, 59. And that would be the length. That would be the length of my vector. So then in R3, what is the length in R3? The norm of in R3. In R3, if in R3, if you have V with V1, V2, V3, then the norm is equal to the square root of V1 squared plus V2 squared plus V3 squared. So whether I'm in the two-dimensional space, I'm just applying the Pythagorean theorem once. In three-dimensional space, I'm applying the Pythagorean theorem twice. And I'm just extending the radical with having the additional component squared being added to the sum of the other squares of components. Now the question becomes, what happens in Rn? What if I have a vector in Rn called V? Then what is the norm of V? Once you head into a higher level dimension, right? The idea of geometry as we know it, it's really difficult to apply. What does it mean to apply the Pythagorean theorem in R5 or in R10? It's not as apparent. But what we do is we just extend the definition. So we're saying, oh wait, so V1 squared plus V2 squared plus V3 squared in R3 works. So then it would make sense to just say, hey, let's just extend this idea then. Because there seems to be some kind of structure, inherent structure in the way norm or distance, quote unquote, works in n-dimensional space. So therefore, the general definition for the norm of a vector in n-dimensional space is as so, the square root of v1 squared plus v2 squared dot 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 vn squared. Okay? So that's the norm in, as we call it, the Euclidean norm in Rn space. Okay. So there's certain properties that have to hold about norm. So we're three major properties. Of a norm or of length. First one, so I should say this first. If V is a vector in Rn, and if C is any scalar, then the norm of V must always be non-negative. Length of a vector is non-negative. Second thing is, if the length of the vector is 0, then this must be if and only if and only if V is the 0 vector. So only the 0 vector has a length of 0. And the last one, if you multiply a scalar to a vector and you want to find the norm of that, it's the same thing as saying the absolute value of a scalar and you multiply by the norm of my vector. So multiplying a scalar, a vector, multiplying a vector by a scalar multiplies its length by the absolute value of the scalar. And many of these can be proven quite quickly just by the very definition, right? The very definition of a norm of a vector is the square root of a quantity. The square root of a quantity can never be less than 0 by the very nature of the square root function. The square root function, if you see in it, it's always positive, non-negative, it's never negative. And the same thing goes for here. How can this ever be 0? If you have a sum of positive things underneath the square root, right? V1 squared plus V2 squared to Vn squared. The only way this is positive, the only way you can add non-negative things together to give you 0 is if all the things are zeros. There's no other way. The moment you have one positive number and you're adding it, it's no longer going to be 0 because all of them will be non-negative. So these two statements here are kind of almost overly obvious as to why they have to be so. Either your length is non-negative, or if your length is 0, then the only way that's possible is if the vector has to be the 0 vector. Now, how would you prove 3 though? Let's prove 3. And a lot of these kind of proofs are very tiny. They're like small, really just algebraic steps that we're applying. So I want to show what I want to show is that if I go from the left-hand side, right, because I can reach the right-hand side somehow. This is kind of reminiscent of those of you who took pre-calculus when you wanted to show that an identity, three identities, right, were true. You wanted to show whether the left-hand side equals the right-hand side. So that's a lot, very much like what we're going to do here. So I want to show that the left-hand side, which is the absolute value of k, or I should say the norm of kv, I want to show that that equals the right-hand side somehow. And when I do that, I'm done. So how would you go about doing this? So we should say if v is v1, v2, right? Vn. So I'm giving a general v in Rn. And k is a scalar. Then what is kv? Kv is kv1, comma kv2, all the way to kvn. Correct? So what would be the norm of kv of k times v? What would be the norm? It would be what? It would be kv1 squared plus kv2 squared plus kvn squared. And then from here on, it's just algebra, really. This becomes what? K squared v1 squared plus k squared v2 squared plus all the way to k squared vn squared, correct? But I still want to show the right-hand side. So how do I show the right-hand side? What can I factor out from each of those terms?
The scalar,
Which scalar?
k.
You mean k squared, right?
Right.
So I can take out the k squared, and what's left? v1 squared plus v2 squared all the way to vn squared. But then what happens with the k squared? Can't I rewrite this as a product? Because this is a product, right? This is recall that the square root of a times b is equal to the square root of a times the square root of b. So that's what I'm applying. I'm considering this as a, and I'm considering this as b. So this becomes what? v1 squared plus v2 squared all the way to vn squared. But what is this? What is the square root of v1 squared plus v2 squared all the way to vn squared? What does that represent?
That's the norm.
That's the norm. This is the norm of v. And then what is the square root of k squared become?
Just k.
No. It's the absolute value of k.
Right.
Be careful with that. And then what is this side though? What is this expression on the right? Isn't this exactly the right-hand side that I originally wanted to show? So I went from the left-hand side, did some algebra, and I got the right-hand side. So guess what? We're done. This is the proof. Very short proof. Not really that exciting in terms of the insight behind the proof, but it's a proof nonetheless. So I proved that if you multiply a scalar to a vector, the norm of that vector is the norm of the vector v without the scalar multiplied by the absolute value of the scalar. Because again, the scalar could be negative. But just because you put a negative, you multiply a vector by a negative, it's not going to necessarily affect the differently the length of a vector as opposed to just multiplying by a positive k. That's why the absolute value here pops up. Okay, good. So a lot of vectors today, a lot of vectors. So we talked about norms of vectors, very important. Along with that notion is this idea of unit vectors. What are unit vectors? They're just simply vectors whose length or magnitude or norm, see all these terminology just starts to jumble up, whose norm equals 1. So I'll give you an example of a vector that's not a unit vector. Let's do 3, 4 again. 3, 4. Yeah, 3, 4 again. So we already talked about this one, didn't we? We know that this vector v, we know that the norm of v was 5. So this is not, so v is not a unit vector. But remember, we can multiply this vector by some kind of scalar so that when you minimize it, you get a vector that's exactly length 1. Now the question becomes, how do we do that? How do we multiply? What would be the vector when you multiply this that gives you a vector of 1? A norm of 1?
It'd be 1/5.
It will be 1/5. So what do you mean by 1/5? You do this. You do 1/5 multiplied by v. So then what would that look like? 1/5, 3, 4, which would be what? 3/5, 4/5. We're gonna call this my unit vector. Let's just make sure that this is true. If this is really my unit vector, what should I get? I should get 1 when I find the vector, the norm, shouldn't I? 3/5 squared is what? 9/25. 4/5 squared is what? 16/25. What do I get in the denominator? I mean numerator, I get 25/25, which is 1. So normally, we denote unit vectors with u. So normally now, from now on, when we use the letter u with the little vector arrow above, we're denoting unit vector, which means that the norm equals 1. So if this is 5 and I take a fifth of it, then I would have 1. Now, how do I generalize this to any vector? So what would be the way for any vector? So if V is the vector v1, v2, all the way to vn, then what we say is then we normalize a vector, we normalize the vector by doing what? The word normalize means to make into a vector, a unit vector. When we normalize a vector, we're creating a unit vector. So what am I going to be multiplying by? What do I multiply V by to get U? If you don't know, go back, close close. Go back to the example we just did. So Sam said, hey, let's divide it by 5. But what was 5 originally? What did 5 represent?
So the inverse of the norm.
It's the 5 represented the norm of the vector. So the moment I have the norm of the vector, what did you do? You divided, or in other words, you multiply by 1 over the norm of the vector to the vector, and you got the unit vector. That's what we did. 5 is really just the norm of V. So I did 1 over the norm of V, multiply that to V, and I get the unit vector U. So if I have a general vector in R-dimensional, in Rn space, if I want to normalize that vector to make it a unit vector, I take that vector V and multiply it by 1 over the norm of V. This is a scalar because the norm of a vector is just a number. It's a scalar. So if I multiply V by 1 over square root of V, then I get my unit vector. So this is the way we normalize our vectors. So let's say I want to normalize V 2 to -1. That's right, Interpreet, very good. So normalize V. Yeah, Tassif, it's not the absolute value per se, even though it's similar to it. It's just the norm, So I want to first find the norm of V. Use the formula, 2 squared plus 2 squared plus -1 squared. I get 4 plus 4 plus 1. I get 9. This is 3. So the norm of V is 3. I want to normalize it, create a unit vector. Another thing that's important to know is that this unit vector is not just that the length is 1, but so this makes it into a unit vector that goes in the same direction. That's also very important. When we normalize vectors, not only do we consider changing the unit length, into being just one single unit, we're also creating a vector that goes in the same direction. That's going to be important when we talk about projections. So the unit vector U that goes along the vector V is 1 over the absolute value, well, it's really the norm of V, multiplied by the vector V. The norm of V is 3. So this will be 1/3 v, which will be 1/3 2 comma -2 -1. Sorry, it should not be -2, it should be +2. So this should be 2/3 comma 2/3 comma -1/3. This is my unit vector in the same direction as the vector 2 comma 2 comma -1. Okay. All